And we're back. We are back to talk about uninhibited radioactive decay. So we were doing these uninhibited exponential growth problems, bacterial growth, and now we're doing uninhibited decay. And remember that the relevant formula is really the same, except this exponent, this growth rate term, will be negative because we are decaying instead of growing. Otherwise, very little changes. So traces of burned wood were found to contain 2.3% the amount of carbon-14 that was originally present, which has a half-life of 5,730 years. So approximately when was the tree cut and burned? This is a pretty standard carbon-14 dating problem. So just a minor bit of information. So you've got the planet. Here's the... Yeah, sure, that's North and South America, kind of. And then you've got Europe. Oh, come on. I'm trying to impress with my drawing skills. Close enough. Fine, there's Earth. Around it is a very thin layer of atmosphere. This is not to scale. So what ends up happening is, in the atmosphere, there's a whole lot of nitrogen, 70% roughly. Solar radiation comes in, hits this nitrogen, and destabilizes it. And a chain of events is set in motion that ends up producing a radioactive form of carbon, radioactive carbon, which then filters down to the Earth, and living things just absorb it. So this carbon is slightly radioactive. It's always being produced in the atmosphere. And so living beings absorb it at a rate proportional to how much there is, which is more or less unchanged. However, once they die, they stop absorbing it, and the radioactive carbon slowly decays. Meaning, compared to a living person, something that's been decaying has less of this radioactive material. It's decaying within the living person as well, but they are also constantly reabsorbing new stuff coming in from the atmosphere, so they're replenishing what they're losing, whereas the dead thing is just releasing it and not absorbing anything new. Okay. Now, what that means is, compared to someone that's currently alive, something that's been dead has less, and if you can measure how much less, you can estimate how long it's been dead. So the tree was burned, and that's when it died, basically. Now, this term half-life, in earlier examples in financial and bacterial models, we talked about doubling time, how long it takes something to get twice as much. This is how long it takes to get 1/2 as much. It's the 1/2ing time. So if you had, for example, 100 grams of carbon-14, after 5,730 years, you'd have 50 grams. After another 5,730 years, you'd have 25 grams. It would half again. So that's what we need to make sense out of all of this. So the half-life is 5,730 years, and it has 2.3% of what was expected. Sorry, let me mute. It's my old Westbury email, and every time a new one comes in, it makes a stupid little noise. There we go, muted. Okay. And remember, our relevant formula here is that the amount of carbon at time t is the amount we started with times e to the kt. So the way we're going to solve this bit here, don't use first. Use this first. The half-life is 5,730 years, okay, to find the value of k. So here is our original formula. Since the half-life is 5,730 years, what we know is, if we plug in 5,730 for time, what we end up with is 1/2 times whatever we started with. Okay, so I just let a of 5,730 be 1/2 a sub 0, but then the right-hand side is just what the formula always is. Okay, so all we did was we took a of 5730 equals a naught e to the k times 5,730. And now, since this got replaced with 1/2 a naught, the a naught's going to cancel. And now I can solve for k by taking the natural log of both sides and dividing by 5,730. And out to, what did they give, 6 decimal points of accuracy, we have here. I shouldn't say 6 decimal points, I should say 6 significant figures. Pardon me. So now we know the value of k. Now we can go back to the original expression, a of t equals a naught e to the k times 5,730. But notice 5,730k is exactly log of 1/2. Okay. So that would give me a log of 1/2 here. Then e to the log of 1/2 gives me just 1/2, and we get out 1/2 a naught. I'm just verifying for you again that yes, we have found the half-life. This is the value of k that is given to us by the half-life. Now we're going to take that value of k and we're going to use it for the other part of the problem. Okay, so now we plug that in for k. So now we know whatever we started with, a sub 0, at an unknown length of time, we have 2.33% of it left. So t is the unknown. That's how long the tree has been dead. And I don't actually know exactly how much carbon-14 it started with. What I know is that it now has 2.33% of what I expected to find. So 2.3% of the amount I started with is how much I have after time t. Now we need to solve this for t. Again, the a naughts cancel out. That's quite handy because we didn't know what number to put there. Take the natural log of both sides, divide out, and we get about 31,000 years. And so this tree was burned about 31,000 years ago. Okay, so another application of exponential functions is Newton's law of cooling. So the scenario here is that you have an object and you place it inside some sort of medium, some sort of environment. And the understanding is the surrounding medium, that environment, is always at the same temperature. No matter what, this is kept at temperature T. Okay? The object inside has varying temperature. For example, your oven is at 350 degrees Fahrenheit and you assume it stays that way, and then you place something inside it that is going to heat up. Now, very, very strictly speaking, as the object heats up, the environment in the oven would cool down. However, you will have some sort of device that when it senses that, it raises the temperature back up by burning gas or turning on an electric element. So you can kind of assume the temperature does stay at the same thing in the environment. You could also use this to model placing something in a water bath, where again, there's some sort of mechanism to make sure the water stays at the same temperature, capital T. Okay. U of t is the temperature of the object at time t. U sub 0 is the temperature that it starts at, and again, k is an unknown constant. Okay, so you should probably copy this formula down. Let me clear off my pen marks because we're going to use it in the next problem. So U of t is the temperature of the object at time t. Capital T is the is the temperature of the surrounding medium, which does not change. U sub 0 is the temperature of the object at time 0, and k is an unknown constant. All right. So imagine you have an object that is heated to 90 degrees Celsius and then cools down in a room and the air temperature is 20 degrees Celsius. Man, I wish today is much hotter. If the temperature of the object after 5 minutes is 75 degrees, when will its temperature be 50 degrees? Now, here is not how you do this. You'd say, well, after 5 minutes, it went from 90 to 75, so it dropped 15 degrees in 5 minutes. In other words, it's dropping 3 degrees per minute. I need it to drop another 25. That's 8 1/3 minutes, just 25 divided by 3. And therefore, after 5 minutes, it was 75. So after another 8 1/3 minutes, it'll be 50. That is wrong. That assumes it changes the same amount of temperature every minute. That's a linear model. But we don't have a linear model, we have an exponential model. So this reasoning just doesn't apply, so don't do it. Okay, use the formula from the previous page. Then determine the elapsed time required for the temperature of the object to hit 35 degrees Celsius, and then make an observation about time passing and getting longer and longer. Consider what happens when t, the time, just keeps going. Okay, so using the formula from 2 slides ago, we take U of t is, capital T is the temperature of the surrounding environment, which was given to be 20. The starting temperature of our object was 90. That's the temperature the object was when it was placed into the air. And K is what I don't know. So we have U of t is 20 plus 70 times e to the kt. Now to find K, we have to use the information we were given. If t is 5, if 5 minutes have elapsed, then the temperature is 75. So we plug that in. Here is U of 5. It's 75. And here's U of 5 using the formula U of t is capital T plus U naught minus t e to the kt. But now the only unknown is k, so we can solve for it. So subtract the 20 to the other side, divide by 70, take a natural log and divide by 5, and you find the value of k. It's about negative 0.0482. So now I can take that value of k, put it back into the expression for Newton's law, and now I can predict the temperature at any time I choose. But I don't want to plug in a specific time. What I want to do is solve for a specific temperature. So instead of setting t to be equal to anything, I still don't know the time, but I let U of t be 50. And here I have my expression for U of t. So I can subtract the 20, divide by 70, take a natural log, and divide by the value of k that we found. And t was measured in minutes, so we end up with about 17.6 minutes. So it took 5 minutes to get to 50 degrees. If it had gone linearly, it would have been a total of 13 1/3 minutes to get down to 50, but this is longer. The reason being, as the temperature of the object gets closer to the temperature of the air, it slows down how fast it changes. So if you had gone with a linear model, you would have been like, oh, it goes to 90, and then it goes to 50. If the function was linear, we'd say after 0 minutes, it's at 90. After 5 minutes, it's at 75, sorry. So I would then draw a line, and this doesn't make any sense at all, because according to this model, the temperature just keeps dropping, but the air was only at 20 degrees. It doesn't make any sense that if I heat something up and I put it in the air, it gets colder and colder until it is absolute freezing cold, and it goes below absolute zero and freezes the entire universe because we modeled our scenario incorrectly. So this is not a linear model. What it will be is an exponential model. Okay. So we'll see exactly how this changes the long-term behavior of the object. The second part of the problem said, find the time when it will reach 35 degrees Celsius. So again, we're just letting the temperature be 35 and time be unknown. Subtract the 20, divide by 70, take a natural log, divide by k, 32 minutes. Okay, it's the same work. All we did was change this value over here to be 35 instead of 50. So what happens as t increases? If you plot this function, U of t equals 20 plus 70 e to the negative 0.0482t. As t gets really big, the exponent gets very big but negative. So what happens to e to a big negative number? This is the same as 1 over e to a big positive number. That's very close to 0. So this bit here is very close to 0, meaning overall you just have 20. And if you plot this function, what you'll see is that it has this as a horizontal asymptote. And if you were to go through the steps of how does this graph, you would do things like, oh, let's do a horizontal reflection and compression, a vertical stretching, but then a vertical shift by 20. So it would take the typical horizontal asymptote of the exponential curve of y equals 0 and shift it up by 20 to y equals 20. So as time goes to infinity, the temperature of the object gets closer and closer to 20, the temperature of the room, but it certainly is never going to go below it. In fact, it's never even going to equal it. Okay, so let's do another example of both. Okay, so I have a compound. It's radioactive. I start with 10 grams. After 6 months, I have 9.81 grams. Okay, it goes into a device which requires, let's say, 8.5 grams to function. When does the device stop functioning? So our information that we have is that we are starting with 10. So that's my amount at time 0. Okay, so our model says the amount at time t is the amount at time 0 times e to the kt. And we are given a sub 0 is 10. We start with 10 grams. After 6 months, we have 9.81 grams. So a of 6 is equal to 9.81, assuming that t is measured in months. If you wanted to measure t in years, this would be a of 1/2. If you wanted to measure it in days, this would be a of 182 or whatever. Okay, and then the question is, what time solves a of t is equal to 8.50? Okay. Now, if you just went straight to the function that models this, let me clear all this out. If you just went straight to the model, you'd say, so our question was, when is a of t equal to 8.50? So you'd say, I want a of t, on the one hand, to be 8.50. On the other hand, I want it to be a sub naught e to the kt. And I know a sub naught is 10. Then I could divide by 10, and we'd get 0.85 is equal to e to the kt. I would take a natural log, and I'd say k times t is equal to the natural log of 0.85. But now I have two unknowns. I do, however, know that t is going to be the natural log of 0.85 over k. I just don't know what k is. But if you did this problem kind of backwards, in other words, you tried to do the second part before you found the value of k, like we just did, don't just throw this out now. You are basically done. We just need to find the value of k, and then we're fine. Okay, so we now know that the solution to the last part is t is the natural log of 0.85 over k. So let's use our given information that t of 6 is 9.81. Sorry, a of 6. So a of 6 is 9.81. So therefore 9.81 must be 10 times e to the kt. Again, divide by 10, get 0.981. Must be equal to e to the kt. Oh, sorry, t is now 6. Take a natural log and get 6 times k is equal to the natural log of 0.981 over 6. Sorry, just like that, but now divide by 6. So k is the natural log of 0.981 over 6. And now I can take this back to what we've already done and said, so for the final part, we want the time t to be the natural log of 0.850 over k, which is the natural log of 0.850 over the natural log of 0.981 over 6, which I can simplify down a little to be 6 log 0.850 over log 0.981. And here's my sort of final exact answer. If you wanted to use a calculator to estimate this, you would end up with, just give me a second, uh, 50.83. Whoops, it's supposed to be back on the pen. 50.83. So after about 51 months, the object will turn off. This is basically how nuclear weapons work and need to be maintained. They work with radioactive material, and if you don't have enough of it, they won't function. And the radioactive material, as soon as you complete construction, even while you're completing construction, it's decaying. You're losing the amount of it. So it's an important question to ask, how long will it continue to function? And people are generally interested in knowing that. Radioactive material is always decaying. There was, I forget what it was. It was some silly, crime procedural. It was like, I don't know, NCIS Los Angeles or something dumb like that. It was on TV. I was slipping through. And the bad guy of the show had been stockpiling radioactive material from a hospital for years. Now, hospitals do have radioactive material. So they need it in order to inject into you so that they can then use a scanner to see where the radioactive material goes to detect what blood vessels are blocked. If it isn't passing to a certain place, they'll be like, oh no, the blood isn't getting there because we injected radioactive stuff into your blood and we can see it's not going there. So hospitals need radioactive stuff. Okay. They actually want stuff with a very short half-life. It needs to decay very quickly. If it's decaying quickly, it's giving off a lot of radiation because they want to be able to inject it into you and actually quickly get a picture of where it's going. If it was barely radioactive, you would need extremely sensitive equipment to pick this up. So they actually want stuff with a fairly short half-life. So they have machines that are capable of making, I think it's technetium, an isotope of that, which decays quite quickly. And the good news about decaying quite quickly is that once it's being generated by this machine, if it's then used, it decays very fast and quickly becomes relatively harmless. So if someone was stockpiling it from hospitals for years and years, when they went to make their nefarious dirty bomb or whatever, most of it would be completely useless because it would have decayed away. Okay, if its half-life is on the order of a couple of days, by the time a year has gone by, it has been cut in half 100 times. It is basically all gone. Anyway, as you learn more, you will have more and more moments of frustration with pop culture that gets math and science wrong. So let's do another example of not radioactive decay. What was the other? Oh, Newton's law of cooling. Okay, so let's do one more of those before going on to the next part of this chapter. So let's suppose I have a water bath which is kept at, let's say, 60 degrees Celsius. I take a metal bar at negative 40 degrees Celsius. Let's not make this water because I don't want it to freeze. We'll call it oil. Okay, I take a metal bar at negative 40 degrees Celsius and place it in. So after 2 hours, the bar is at, let's call it 30 degrees Celsius. When will it reach 50 degrees Celsius? And remember our generic formula for Newton's law of cooling, U of t is a capital T plus parenthesis, U naught minus t, e to the kt. So we have to identify some givens here. 60 is the environment of the medium, capital T. Negative 40 is the starting temperature of my object, U naught. After 2 hours, it is 30 degrees Celsius. So U of 2 is equal to 30. So let's take all of that information and put it in here. So U of 2 is equal to 30. But that's also going to be capital T, 60, plus U naught, negative 40, minus T, minus 60, E to the K, which is unknown, and then T is 2. Okay, now here, pardon me, we're going to end up with a slight problem. No, sorry, we won't. So we can solve this. So we subtract 60 from both sides, and we'll end up with negative 30 is equal to negative 100 e to the 2k. Divide by negative 100, and you'll get 0.3 is equal to e to the 2k. Take a natural log. 2k is equal to the natural log of 0.3. Divide by 2. K is the natural log of 0.3 over 2, which we can go ahead and round off to natural log of 0.3 by 2 is about negative 0.6020. Yeah, negative 0.6020. So now I know my value of K. Then the question becomes, when does it reach 50 degrees? So remember that in order to apply this formula, we have capital T is equal to 60, and now we know that K is about negative 0.6020, and we want to solve when is U equal to 50. So our Newton's law of cooling formula was U of T is equal to capital T plus U naught minus T e to the KT. We know that capital T is 60. U naught was negative 40. And now we know the value of K is negative 6020 times T. But now we want U of T to equal 50. So stick that there, subtract 60. Divide by negative 100. Take a natural log. And divide. And that estimates down to, that's my phone, sorry, log of 0.1 over negative 0.6020, and we have about 3.82. Okay, so these radioactive decay and Newton's law of cooling and financial model problems and bacterial growth all follow a very similar pattern in what sort of steps you do. Okay. So after this, we will go on to logistic models, which work a little bit differently, but fundamentally are using exponential equations.